Edison conferred with Upton about the necessity of making a new kind of pump, a pump in which he could measure the vacuum and perhaps also lessen the time it took in taking the air from the globes. Well, the result was that in about a week or 10 days, we had 3 such pumps. The Edison combination of the Sprengler and the Geissler. The operation of this pump is as follows. First, we set the Sprengel in operation. Now you see the mercury coming down here, taking out the air. And the mercury falling in that jar there has to be replaced, as I have already shown you, up and carried up and poured into the reservoir. The Geissler part of the pump is operated this way. I am now displacing the air here. As you see, the mercury is forcing the air out, and it bubbles down there as it comes out. Now it'll pass over here. Now I let it down, and there is a very good vacuum already. I open this stopcock, and you notice how the column rose here. And that way it went on until the quantity of air here was of no account, and then we stopped this part and let the Sprengel work. To test the vacuum, we did something like this. We forced the mercury in that globe and then calculated how much air in this tube remained. With this pump we got a vacuum that was up to 1/1,000,000th of an atmosphere. It was with these pumps that the first batch of Bristol board lamps were made. They were the lamps that served for the great demonstration in 1879 during the latter part of December. We might say this is the first experimental lamp factory that ever existed. And as for mass production, we were able to make about 25 lamps or 24 lamps in 24 hours. As you see, we have here 2 lamps. Sometimes when more lamps were available, we put on 3. And that way the pump went on and served for a long time. It was in the early part of 1880 that Edison said to me one day he thought it was about time to get to work and make a simple vacuum pump that would be efficient commercially. He said that the combination Sprengel and Geissler pump was simply prohibitive to use in commercial work, whereas the Sprengel pump itself, with all this glass here, with ground stopcocks, ground connections here and here, that too must be eliminated. We can't keep an army of expert glass blowers to make the pumps and keep them in repair. We want something simple that a medium glass blower can make by the dozens. Go to work, Francis, and see what you can do. And he gave me instructions. And the result was that in 2 or 3 weeks, Edison constantly inspecting my work, we finished a pump like this here. Here we have no ground connection. A simple piece of rubber put in, shoved in here, a little bit of mercury. That's the whole pump. Well, and I showed Mr. Edison that we attained a very high vacuum. Well, said Mr. Edison, now Francis, go and have them put on a chamber with the phosphoric anhydride. That was done, and here we have the pump. The pump that the Edison electric light companies and lamp companies, both in America and in Europe, used for more than 30 years until better processes came into use. Simple. A young man taken in the glass blowing department in about 2 weeks. Training could make the pump. Thousands of these pumps lined the hall in the lamp factory, each one having a lamp. The reservoir consisted of a tank of mercury in which the mercury was lifted, passed along an iron pipe, and then at each place a rubber tubing was connected to the lamp, while the outflow also went into an iron pipe, and an Archimedes screw lifted the mercury up to the reservoir. Such was the simplification and help in the manufacturing of lamps to make them a public commodity. When Edison made his first practical lamp in October 1879, he naturally wanted to know how much energy an incandescent lamp of that kind would consume. And so it happened. While we were making lamps from Bristol cardboard, that one day Edison came and asked Mr. Upton how to determine how much energy the lamp would require to keep it up to 16 candle power. In those days, we had no direct reading voltmeter nor ampere meter. It was a tedious process to determine the amperes or the volts. So after lots of thinking about and conferring with several professors in university, Upton decided to use the calorimeter method. In an instrument like this, we placed a certain amount of water and then put in a little ice in order to get the water below about 10 degrees below the atmosphere of the room. And then we had our lamp here, a thermometer here, and inserted the lamp in the water and connected it to the mains, to the current. And then let the current heat the water, the lamp heat the water. Noting the rise of temperature on our thermometer, we generally stopped when the temperature of about 10 degrees above the temperature of the room was reached. Then we weighed our water carefully, and from the number of degrees that the water was heated, we calculated the foot-pounds of energy, the mechanical foot-pounds the lamp required. And so it happened, we would say that a lamp requires 2,000 or so foot-pounds of energy to bring it up to 16 candle power. It was only in 1882 when Sir William Siemens in London proposed that the watt 1 ampere multiplied with 1 volt should be designated as a unit of energy. And then it was easier sailing.